Hello, my name is Kai Mitchell, and today I'll be presenting my Lab 2. Coulomb law states that the electric force between two charged objects is directly proportional to the charge of objects and inversely proportional to the distance squared between the two objects. The electric force between two objects is a non-contact force that acts over a distance of separation. In this lab, we will examine, model, and apply Coulomb's law in order to determine the charge of a piece of tape. To do this, we will also apply Newton's second law, which states that the acceleration of an object is dependent upon the net force acting on an object and the mass of the object. In this case, the two forces that will be acting on our model is the gravitational force expressed as the weight of an object and the electric force. In this lab, we will be looking at a method of calculating the electric charge of a charged object and how to improve this measurement. The goal of experiment 1 was to estimate the charge of a charged tape using the assumption of equilibrium between the gravitational force and electric force, as we treated each of the pieces of tape as point charges. In Lab 2, we will still be making an estimate of the charge of the piece of tape, but by modeling each piece of tape as a line of infinitely small pieces of tape, each with their own point charge. Here are some of the fundamental physics that are exemplified in this experiment. Newton's third law states that for every action there is an equal and opposite reaction. This is exemplified in our experiment in that the top tape and bottom tape exert equal and opposite forces on each other. Newton's second law states that the system in equilibrium has a net sum of forces equal to 0, which we can assume that only the two forces acting on the top piece of tape are the gravitational force and electric force due to the bottom tape. Charge can be computed by first determining the electric force on an object and then using Coulomb's law, which states that the electric force equals the electric field times the charge. Additionally, the reason our experiment is more accurate when we include multiple point charges can be proven with simple calculus in the sum of infinite series that equates to taking the limit as a series as it goes to infinity, which becomes more and more accurate. The experiment was the same in Lab 1, where I charged two pieces of tape by ripping them off from one another, and I placed one of the pieces of tape above two supports and held each side of the piece of tape until it floated and stayed there, and I could record the distance. Now onto the data. The piece of tape was 0.2 meters long, and the piece of tape was 0.2 meters long, and that the mass of the tape was 0.002 kilograms, and the displacement between the top piece of tape and the bottom piece of tape was 0.15 meters. When using the principle that the electric force equals the electric field times the charge and setting that equal to the gravitational force mass, I was able to determine that the magnitude of charge on each piece of tape was 7 times 10 to the negative 9 coulombs, which this value was calculated in Lab 1. I then used VPython in this lab to model each piece of tape as a line charge instead of a point charge. I used that starter code for Lab 2 and updated it with my values for the mass of the tape and estimate the charge I calculated in Lab 1 of my project. I then added my function that creates an E-field based on a charged particle in an observation location. This function was part of Lab 0, and I used this code from there and updated the variables to match the current lab. On line 62 and 63, I updated the starting position of the top tape to be 0.15 meters in the y direction, which is the total displacement between the two pieces of tape. I then gave each piece of tape a length of 0.2 meters in the x direction. I then adjusted my scale values based on the look of my Visual Python output so that the electric force arrows matched the gravitational force arrows. This section of code iterates through every piece of charge on each piece of tape and calculates the electric force on the top tape due to the bottom tape, and creates an individual force arrows based on the electric field along with the inputted charge at each of these locations. Finally, the two large net electric force and gravitational force arrows are constructed, and the magnitudes of each are printed out. After running the code, I got this visual representation where the green arrows represent the individual electric forces on the bottom tape, the red balls represent the top pieces of tape, and the blue balls represent the bottom piece of tape, whereas the white arrow represents the net electric force by the bottom tape and the top tape, and the yellow arrow represents the net gravitational force on the top tape. I plugged the value in of the charge that I calculated from Lab 1 into Lab 2, and I saw that there was a magnitude of electric force of only 2.73 times 10 to the negative 4 newtons. However, stated before in lab when we modeled each piece of tape as a point charge, but they were modeled as lines of charge, and so it's seen that the magnitude of the electric force is much too small to balance out the gravitational force. After playing around with the value of charge, I got an estimated net charge on one of the pieces of tape to be 1.88 times 10 to the negative 8 coulombs, and I was able to confirm this number by running the code and visually seeing that the output of the code shows extremely close to the values of the gravitational force and electric force. Now for the conclusion, if I modeled each of the tastes as a single point charge, I did in lab, I got 7.10 times 10 to the negative 9 coulombs, as opposed to my more accurate value of 1.787 times 10 to the negative 8 coulombs based on the continuous charge model. These estimates differ because there is a non-negligible component in the lines of charge method, which the point charge method, whereas the y component of the electric field is only the force considered in equalizing the gravitational force. This makes sense that the continuous charge required a larger charge to balance out gravitational force, as not all of the force was straight up in the y direction. The charges of the line charge method is much more accurate as a model for a real-life phenomena as opposed to a crude estimate. Thank you for learning physics with me, and I hope to see you next time. Bye!